Well, good afternoon, everybody. My name is Rudy Shankar, and welcome to the Spring Seminar Series at Lehigh University, hosted by the Energy Systems Engineering Department. So this is the second lecture that we'll have this spring, and we have Revis James, who presented the first. And this will be a continuation of a very fascinating subject, energy technology and policy. And last time he spoke, almost a month ago, he laid the groundwork for why there needs to be flexible operations throughout our grid and what some of the variants, what the impacts could be. And today's talk is going to center around, what could be potential game changers for a sustainable portfolio. So background on Revis, he was a vice president for policy planning and development at the Nuclear Energy Institute. And before that, he was the director for the Electric Power Research Institute. And as the director of the Center for Technology Assessment, he focused on strategic R&D priorities for the electric power industry. So he's got a lot of experience in this field, and we are lucky to be able to share that. Thank you, Revis. Revis spent 2.5 years in Paris, France. He was part of the team between EPRI and Electricité de France. And I worked a lot with Revis, and I really enjoyed working with him over the past years, and I really look forward to this lecture. Revis, the floor is yours.
Thanks, Ramesh. Appreciate it. I'm going to quickly just switch over to the beginning of my presentation and like to make a few opening remarks. So allow me to do that for just a moment. So if you could confirm for me, Ramesh, that everyone sees the presentation?
Not yet.
Okay. All right. Let me go back to Zoom and make sure I'm sharing my content. Stand by. Okay. Oh, there we go. I missed a step. Sorry about that, folks, but I think this should work. How about now?
Yep.
Okay, very good. Excellent. So thanks again. I appreciate everyone who's here. So what I'd like to do is just briefly recap a little bit, just to create some connection between the seminar I gave last fall as well as the one I gave earlier, about a month ago. The scope of research and priorities I've been talking about is the need to create a sustainable electric power generation portfolio. And as some of you who were on the previous call may recall, sustainable is a rather holistic term as I'm using it, not solely from the perspective of environmental impact, but also from the perspective of economic sustainability and technological sustainability. And as we'll discuss, the operational flexibility issues that we talked about in the last seminar, which illustrated some of the complexities of achieving a sustainable portfolio, is really an important aspect, but only one aspect of several challenging issues that, if addressed or resolved or mitigated, could really make a major difference in putting us in a position to have a sustainable portfolio in light of all the challenges that we face. Climate change is one that we all think about, but of course, we will experience long-term power growth because ultimately over multi-decades or that's more than a century, it's ultimately proportional to population. So something else I'd like to just note here is that I will kind of use some terms interchangeably throughout my talk here. I often say a power generation portfolio because I want to refer to the collection of the entire generation fleet with all the different types of generation assets that we have. I'll also say asset mix or generation portfolio to refer to that same group. And the perspective here is looking at the entire power fleet. And a lot of you will be thinking to yourselves, well, the fleet is owned and operated by many different stakeholders and isn't really an entity that can be controlled by a singular authority. And that's a true statement. So part of the challenges here, and we'll discuss this, is how to achieve sustainability in light of the fact there are so many stakeholders. And so we'll talk about that a little bit more. So having said all that, I think an interesting way to look at this is to look at some of the areas where we have challenges or barriers to achieving the sustainability, and then ask the question, what types of game-changing developments would mitigate or eliminate those barriers? So let me move on. So first of all, just a quick recap from the last talk here again. A lot of discussion that's happened previously as it relates to this area. Let me back up a second. Many aspects of the sustainability are, of course, recognized. It isn't like this is an unrecognized issue, but it's so challenging and so multidimensional that some of the issues around sustainability have not really been addressed to a great degree. And historically, what has happened is the multiple stakeholders that exist in the area, regulators, consumers, asset owners, investors, advocacy groups who are interested in pursuing particular technologies for various reasons. The way that those issues have been addressed is to try and address economic and policy structures which affect how we generate and deliver electricity. So market design, electric power market design and deregulation is a major area. Creating tax incentives, for example, production tax credits for renewables. And to some extent, those measures have been effective. However, I think what has tended to happen, and now I'm perhaps offering a viewpoint here, is that we've shied away somewhat from some of the more difficult technical problems that will require sustained effort to address those. And yet those technical issues, I think, are maybe more the core opportunities that would really allow us to create a sustainable power generation sector. So I'm going to try to focus a little bit more maybe on the technology perspective here as we go through this, even though there are really many other aspects of measures that can be taken or strategies that can be employed to try and address the sustainability issue. I don't want to suggest that only technology can solve this, but I think that the technology issues are particularly challenging and deserve some focused attention. So let's move on from that. So what I've done here is I've just shown you a chart. I used it last week or last month. And this is a somewhat older chart, but it just illustrates a point. This was a chart EPRI put together back in the 2010-11 timeframe. And the idea was to illustrate when you think about the major technologies that provide electricity, and that's the columns here, coal with CO2 capture and storage, natural gas, nuclear power, hydroelectric energy, wind and biomass, geothermal and solar power. You can see that these, and then in the rows, you see different important characteristics, which, if optimized, would certainly increase our flexibility in terms of dealing with all the multiple challenges that we need to address for a sustainable portfolio. Construction cost obviously is one of them. That capital outlay is, in fact, probably the most focused upon area historically. The production cost of electricity over the lifetime of an asset. To a lesser extent, although recognize the amount of land and water resources that are required for a particular technology as another issue. Of course, CO2 emissions themselves and other emissions are important from an environmental perspective. Managing the waste streams from power plants is another issue. And then, of course, very importantly, the availability of assets that are consistently available when needed, regardless of weather conditions or electricity demand, and so on. And then finally, this aspect of flexibility that we dived into a little bit during last month's talk. And the green circles kind of illustrate a qualitative assessment of where technologies are particularly strong in addressing a particular area. And the more yellow suggests those technologies experience more challenges in those areas. And you can see there's a healthy distribution of green and yellow circles throughout. So there really isn't a single technology that addresses everything, nor is there, an issue for which all technologies are able to address that issue. And this kind of just illustrates the quandary. And so I just thought I'd use this as a way to orient our thinking here as we look into some more specific challenges that might give us an insight to where some real game changers could emerge. So one way to think about this, I think, is to talk about really the underlying. I use the term key challenges here on the slide, but I think almost like the underlying assumed boundary conditions that we have to work under in the power sector. We need electricity for the indefinite future. The infrastructure will be here for a very, very, very long time. Essentially, whatever we do to address any aspect of sustainability has to be a solution that we can envision as being an indefinite solution. That's obviously very challenging. So that's that lifetime and the management of that, looking at not only how things can work, how cost effective or efficient they are, but envisioning how those technologies or those assets will transition into a long-term future and remain viable is an important part of thinking about some of the issues here. Another part of it is simply that the demand for electricity and the patterns for when demand is high and low vary substantially, as many of you are familiar with that, not only in daily and seasonally, but between consumption sectors. The industrial sector and the residential sector, the commercial sectors are different, and they are individually changing for a variety of different reasons. We'll talk a little bit more later here, but obviously the emergence of distributed generation or distributed power generation is creating differences in these patterns. So contending with these different consumption patterns, yet having a power generation fleet which is capable of remaining reliable, not incurring an undue operational costs, is challenging, very challenging. We saw that with the flexible operations discussion in the last seminar, but there are other aspects of that make it quite challenging. And when you look into the long-term future and consider how additional variability could emerge in the pattern of consumption, that is another very important challenge. It's a fundamental underlying issue in looking at the power generation fleet. The third issue, of course, is not maybe a technical issue per se, but it creates technical challenges, and that's simply the fact that different stakeholders have different priorities. They want different things. Some investors may not really be interested necessarily in really long-term sustainability because their time for recovery of their investments is shorter, much shorter. A utility company, for example, might want very high reliability and very high maintainability, of course, high levels of safety. So, for example, they would prefer to operate some assets with constant power output, even though flexible operations is a necessary capability. And of course, in fact, I think I'll skip over this next one and come back to it as the last bullet, because I want to talk about that a little bit more depth. So let's go on to this competition for resources in the non-power sectors of the economy. That's another facet of a power generation which is emerging to be a greater and greater challenge, and that is, by non-power sectors, I mean the fact that land, water, and even some of the fuels are needed for non-electricity purposes. And as the power sector has grown, that competition has created some difficulties in terms of how to continue to provide electricity in all the aspects of sustainability that we've been discussing, yet recognizing the need of these other sectors for these resources. Obvious examples would be, for example, substantial amounts of land or areas of the ocean where you would have wind farms. And many are aware, of course, in some cases there have been opposition to wind farms due to the use of those resources. Another issue, which has long been a challenge for thermal power generation, so that would be true of coal or nuclear, would be the fact you have to have an ultimate heat sink, a place to ultimately reject waste heat, and therefore you need a body of water. And that is a resource, and that is also an area of increased competition, especially if we have to expand our fleet, which we most certainly will if you look on the 100-year time frame and beyond. And then another important facet of that is simply fuel itself, natural gas. And for much of the time I was in my career, the non-power use of natural gas was dominated the total consumption of natural gas in the United States. That's no longer true. The power sector consumes gas on a scale which is comparable to our non-power uses of gas. And when we face situations where there are high needs for gas in both power and non-power applications, resolution of that competition is complicated and has technical and non-technical aspects to it. As I mentioned several times, obviously, as we look long term, the time scales over which the sustainability should be sustained, we will certainly see growth in electricity consumption. Another driver of that growth may also be not just simply the growth in the number of people and levels of economic activity, but also that there may be strategies around environmental issues that promote more electricity consumption. As some of you may be familiar, many of the economic analyses have looked at ways to decarbonize the economy and address climate change in a most cost-efficient manner, come to the conclusion that increasing electricity consumption and displacing non-electricity consumption for power production, for power use, creates an opportunity to first decarbonize the electric sector and then transfer effectively that decarbonization to other areas by getting those other areas of the economy to use electricity. So that's another reason why we can expect some growth. And let me come back now to this final item here, the necessity of just-in-time power delivery. This is a profoundly important feature of the system, as many of you are aware. As long as we have to produce electricity and vary its output in proportion to demand, that creates many operational and technology challenges that have to be consistently met. And if we were able to decouple to some degree production and consumption, that opens up many possibilities for increasing the sustainability of the portfolio. So I think that's an area that's worthy of thought. So if you think about all of these challenges as a group, each of them individually implies many subsidiary challenges that are quite substantial. If you think about these challenges and then ask some questions, well, what if we could do this, or what could we do to mitigate or eliminate some of these issues? I think some interesting things emerge. And so I've taken a shot at that based on not only on prior research I was involved with in my career, but also from my own perspectives. I will not say that what I'm doing here is comprehensive. I'm certain that with more depth and more thought, each of these challenges and others could be identified that flesh out the suite of different opportunities for game changers. But I think this what I've done here maybe is a way to get the conversation going. And I think we'll have some discussion time here at the end to talk about that. So let's just look at each of these in a little bit more individual depth and think about them. One would be the long time horizons. And just an observation, I think I brought this up maybe in one of the two previous seminars I've done. This is not unique. We have other infrastructures that require very long time sustainability. Our transportation infrastructure, since we don't have a rail system in this country that's extensive enough to be the primary distribution system, we rely on the road system and the distribution of goods and services through that road system. And so it's an essential infrastructure. It essentially requires an indefinite level of support and viability. Our water management system is another example of that. Obviously water treatment, but also eventually we may be facing desalination and other needs to address the depletion of our freshwater resources, and sustainable agriculture, meeting increasing demand for food while managing land resources in order to be able to sustain the increasing levels of production that are going to be needed. That's becoming more and more important. And the concerns about climate change and greenhouse gas emissions has added an additional degree of complexity in that. So we have this problem in other infrastructures, and so the power sector is not unique, and therefore I don't think we need to look at this as a problem that is fundamentally insolvable. It's simply a matter of mitigation and how to mitigate effectively. The other aspect of this I think it's real important to talk about here is that very often in looking at the implications of very long-term sustainability, priorities change. Investments or technology development or technology deployment that might not seem as important if one is thinking about the next 10 or 20 or even 30 years become more important when you pose the condition that we need long-term sustainability. And that's not always a recognized aspect of things when you're talking to stakeholders outside the technical community. So that creates this need for a constant level of communications to constantly create consciousness in the stakeholder community, so that as all those different groups I mentioned previously, about the need to balance resolution of issues that emerge more over the long term than issues that are only immediately identifiable in the relatively near term. So having said those things, this comes back to earlier presentations that I've done about how important it is to create some sort of framework in which it's observable, the implications of these long time horizons and the priorities that emerge from them, so that they can be balanced against near-term priorities, which have to be addressed, whether it's economic priorities or regulatory priorities and so on. And this energy economic modeling that I was trying to describe in some depth last time is a very, very valuable tool in creating these frameworks. As I said in those previous talks, it's important to recognize the value of this modeling is not to be predictive, but to create a framework in which the different stakeholders can communicate and come to some sort of consensus around what is going to be done about certain issues and how to balance certain priorities. It's a framework which creates a consistent platform on which to have those kind of discussions, and it enables the technical community to communicate with the other stakeholder groups about where the trade-offs and opportunities exist. So that's a very important, I think, opportunity to create a game changer if we're able to create that platform in such a way that that there's recognition across different stakeholder groups. This is the basis on which some of these priorities need to be discussed, and individual stakeholders who are trying to advance their interests can resolve issues. So that's a big challenge, a very big challenge to achieve that kind of consensus view of how to frame these questions. But it would be very, very powerful if we're able to achieve that. Another facet of these long time horizons sounds mundane, but yet it's by no means simple, is extending the lifetime of assets, enabling us to rely on our fleet longer so that we are not constantly posed with the turnover, the cost, and technological barriers with turning over assets. And just briefly, right now, for example, there's obviously different viewpoints on the viability and role of nuclear power in the future power fleet. But if we do expand nuclear power in the longer term, we haven't been building a lot of nuclear plants in the recent past, in the last 20, 30 years, although we do have a few projects going. So our ability to do that well, efficiently, effectively has deteriorated somewhat. And we're relearning that through the handful of projects that are underway. So this is another reason why I think extending asset lifetimes creates less of a boom-bust rhythm in how the power fleet turns over, and therefore allows us to maybe in a more orderly fashion retain and develop our capabilities to develop and deploy different technologies. So, to that end, obviously, some of the work that's going on now in life extension of nuclear power plants, doing technical work to show that a power plant can operate for 80 years instead of 60, or 100 years instead of 80. With solar and wind facilities, because comparatively there are new technologies on a grid scale, not a lot is really known about what the lifetimes of these facilities are. During the time I was working, often 20 years we talked about as sort of a nominal number, but there wasn't really anywhere near the body of information or research to establish what those asset lifetimes would be. And it's very important that we understand that better and then make sure they're long. And there are undoubtedly technical challenges there. And since renewables will be playing a larger and larger role in our future, given their value in terms of no fuel cost and their positive environmental characteristics, this is critical. Another area, again, it's very important from an asset lifetime standpoint, is extending the life of natural gas combined cycle plants. Now, natural gas combined cycle is valuable uniquely as opposed to just simple cycle turbines, because you get a higher energy density and you have some positive environmental impacts of that. But the ability to operate those plants for long periods of time, 40, 60 plus years, has not generally been demonstrated. It's a focus of the area now. That's been emergent for the last decade. And some of you may remember I made reference to a few different technical issues that arise when you try to run these assets longer and also with some flexibility. Even though we rely on our natural gas fleet generally as the primary source of operational flexibility in the overall fleet, the design of these assets still have some challenges as it relates to flexible operations. So focusing on asset lifetime extension, which has already been an important focus in the R&D community, is still a very important priority, because it increases the optionality that we have to address other issues is while we're able to use the fleet that we have. So it gives us more time optionality. So that's very, very essential. So time horizons is one thing. Okay. So, but there are several other dimensions here. And so let's look at demand patterns, the variation in demand patterns. For the bulk of our fleet, the primary generation, gas, coal, and nuclear, from a power plant standpoint, establishing an output level and maintaining that level, a fairly constant level of output, this is a general statement, and you could take issue with this statement for some specific assets and specific situations, but broadly speaking, most of the history of our power fleet has been designed upon the idea that you want to optimize the efficiency of the asset, and therefore you want to create operational conditions which maximize efficiency and maximize our asset life. Well, that tends to translate to a constant output level. And that, as we talked about last time, isn't necessarily what our future holds. And also I would think it's fair to say that historically, perhaps, the different operational roles that different assets play in the overall fleet was maybe less recognized than looking at each asset individually and saying, how can I make this asset as efficient as possible? Now, as we have a much more complex and interconnected grid, and we have a complex economy that creates different consumption patterns, different assets have to provide different important roles, and we have to understand their design and deployment, recognizing what their role is going to be. So, for example, as I said earlier, natural gas plants have essentially become the flexible asset, a flexible resource in the overall fleet, even though they're not uniformly distributed everywhere in the system necessarily. So not all areas of the country have the same levels of natural gas availability for flexible operations. So that's a problem. This basic idea that our power plants necessarily don't like any mode of operation other than a mode that is optimal for the power plant. How can we address that issue? Another thing is, as I said earlier, these consumption sectors vary in their different patterns of demand. And I just wanted to add the comment that in addition to the typical daily variability and seasonal variability, you have variability by region. Different parts of the country, you see different patterns, not just solely due to the consumption within that region, but due to the degree to which energy is moving in and out of that region with other regions. And so the level of connectivity between different control areas, or even different interconnects, the major interconnects that constitute the overall transmission network, that creates some variability. And that's likely to increase in the future because the ability to move energy between regions is likely to play a role in how we cope with the added need for operational flexibility. Distributed generation is another feature that adds variability. Most of those assets are owned by customers, and those customers will operate those assets in a manner which are beneficial to them and their interests. Whether it's availability and reliability, or it's economic, costs, or even profitability. So how those assets are used, and may or may not contribute positively to how the fleet operates in terms of dealing with demand variability. So that could add variability. And I already mentioned the interregional energy transfers. So having said all of those things, the degree to which we can create operational flexibility for any particular type of asset, or to create a fleet which has more flexibility, is a very, very high priority. And some of the results of the study that I was using to illustrate those points in the last seminar go more in depth into the kinds of added capabilities that could be created either within the assets or in terms of transmission characteristics to enable that. But that's a very important priority, is to how can we create the flexibility to essentially enable this continued variation in demand patterns. The idea, therefore, is not really let's eliminate variation in demand, but rather let's simply accommodate it and figure out a way to cope with that. And that may translate to higher cost for energy, essentially, because that's an added capability which could create costs. Another area here is the stakeholder priorities and the competition for interest. And I kind of referred to some of the different facets of how people think about things. I think that the challenge here ties back earlier to references I was making to this framework in which we can talk amongst stakeholders. We need a way to explore what kinds of combinations of policies and technology and regulatory features can combine to create an environment in which stakeholder interests are met, yet we achieve core, overarching requirements about environmental impact or cost or safety. We need that. This just emphasizes the need for that framework. Now, partly in the past, looking at asset costs and looking at how to make assets more reliable and maintainable, and being able to develop and deploy environmental controls that are effective and so on. That's a part of that problem that creates technology capabilities to address that. But understanding where the trade-offs exist between regulatory choices and policy choices. And I separate those two because policy choices could relate to incentives and things other than regulation, and technology deployment. Understanding how to combine different optionality in those areas, you need a framework in which to do that. And again, kind of come back to this modeling, energy economic modeling. And there's some needs in that area that I'll come to here later. Where we are with modeling is tremendous steps have been made, but that modeling area historically, I think, is focused first on just least cost. How do we create electricity at the lowest cost, and how can we understand that across an entire fleet? And then secondarily, how to achieve least cost electricity production in light of various regulatory constraints that exist. Now, I think these tools can be expanded to ask broader questions about if we want a certain level of operational flexibility, or if we want a certain ability to move energy between regions, what advantages that provide. I think these tools are beginning to be looked at as an avenue for looking at some of these other issues. And that's where I think a challenge lies here. And these different stakeholders are always going to be pursuing their interests. I think the only issue we can do here is create a platform in which communication can occur and consensus and compromise can be achieved. Now, the arbiters of that consensus building may be policymakers, or may be regulators, or other institutions that act as a sort of a referee on how we operate the system, like the different state groups which oversee the electricity grid, or NERC and groups like that. But we need that platform is badly needed, and enhancements in that is badly needed. So this area of competing stakeholder priorities is an important, I would say, non-technical issue, but it creates some implications for technology development and for analysis and modeling. And then, of course, we come to the just-in-time power delivery. I probably should have put this last because it's probably, in some sense, one of the most challenging parts of the whole thing. But we have a system here in the United States where essentially, and this is interesting, this number hasn't changed a lot for several years, even though we've had some assets have come and gone. And that is that we really have the ability to store about 2% of what we can generate in our system. Pumped hydro primarily, and to some lesser other smaller scale technologies which can store energy and then put energy back into the grid when needed. But effectively, our system is almost without storage, which means we are a just-in-time delivery system. In contrast, for example, Europe, which is a smaller system, and there's some other characteristics for why it's different, but it has about 7% in their system, which helps. They're still certainly far from being a system where they can simply ignore demand when they choose when to generate energy. But basically, we have this instantaneous demand, and that leads to all kinds of other underlying challenges. Resource planning, resource adequacy, knowing that you have enough asset generation at any time, ensuring that's true, defining requirements for adequacy and resource availability. All of those areas are complicated by the fact we have this just-in-time power delivery system. This just-in-time system exacerbates the operational flexibility challenges that we were talking about in the last seminar, because with just-in-time delivery, variation, transfer to the generation side almost immediately. Were you able to buffer the variation in demand because you had more storage or some other resource? You could perhaps limit the challenges that operational flexibility creates. And the planning requirements that emerge from this just-in-time delivery environment are complicated. The operation between control areas, the different control areas in the country, and through the major interconnects, coordination, dealing with major upset conditions, and we've all seen examples of that in recent, further back past of weather events and other things which create challenges. Those requirements for that planning are really complicated, and in the face of all these stakeholders, implementing plans which anticipate challenges related to just-in-time power delivery are difficult. So obviously the question is, can we decouple generation from demand? Is that possible? What could happen? And there are a lot of challenges there, but it's worthy of consideration. One is, of course, scaling up our energy storage capabilities. Even if there are substantial costs that are needed, there are some tremendous benefits that would result. You would need storage, though, that has certain characteristics. Our system and its variability, variation occurs in minutes and seconds. So large amounts of energy would have to be capable of discharge into the system in those timeframes. And unlikely you would see those type of events of storing energy and then putting energy back in the system. That would happen frequently throughout months and years. So our technologies for doing that would have to accommodate high levels of this cycling. Obviously, many of us have talked, we've all advanced battery research, and there are some concepts like ultracapacitors, things that have been done to sort of strategically put targeted amounts of energy storage, smaller amounts at strategic places in the system to allow us to manage transmission operations better. That has evolved over time, but basically this ability to buffer the generation from demand does not really exist. So another remedy to help mitigate this might not be to just store energy, but to simply increase more ability to move energy around the system more easily, so that we are able to utilize what we do have and not have these isolated areas, say, within the system that are experiencing greater challenges. That leads to, obviously, more transmission, more efficient transmission lines, different topology. All those questions arise when you ask, how can we mitigate this just-in-time issue? And a third strategy that possibly is worthy of consideration, and it has been done, I think, on some small scales in the country, but it has not yet been deployed, I think, on a broad scale as a strategy to deal with whole grids challenge with just-in-time delivery, is the idea of taking distributed energy resources or actual electricity loads and aggregating them and coordinated control of those aggregated resources and loads to effectively create, I guess I would sort of say, a negative power plant, a plant that can not consume energy based on how they're controlled, so that you could reduce the impact on generation from changes in demand. Obviously, on a very small scale, we've seen this. We get a call from Duke Energy or somebody who says, "Can we put something in your house to lower your or to raise your air conditioner set point by a half a degree for an hour on certain days of the year?" That's the same concept, but scaled up over a much broader array of assets, could potentially create essentially a way to take a piece of demand and make it dispatchable, if you would want to think of it in that way. And that would allow us to then again buffer the demand on generation from the demand for electricity. That's those are all very challenging areas, but the benefits could be profound. For example, just the benefits on cost and reliability alone, if we were able to operate all of our assets in a manner which is optimum from the standpoint of asset life and efficiency, and with less consideration for when the energy is needed, because of some strategy that allows us to decouple, we would lower the cost of our electricity production. We would extend the life of assets. We would likely positively affect all the environmental impacts. There are many, many benefits to that. So this is a big challenge, but well worth consideration. Competition for resources, land, water, even fuel. I talked about that at some length earlier. One of the another issue in these resources is where you put things. Historically, our transmission network and where the consumption centers are, and how far away you can be from where the consumption centers are, impacts where you place assets. Natural gas combined cycle in particular, because it's producing both electricity and thermal heat, needs to be somewhere where that thermal heat can be delivered to the application that needs it. So what all that suggests is, we will not, I don't think we'll ever be able to eliminate the need of these other resources to support the ability to generate electricity, but you can ask the question, how can we reduce the need for those resources? So one way of doing that would simply be to increase the energy density of whatever asset you're using. So for a given amount of land or area, or a given amount of access to a water as an ultimate heat sink, if we can generate more energy, then we can, ultimately reduce the amount of resource needs for power generation, and then reduce the competition for use of those resources for other things in our economy. So, one choice obviously is to choose technologies that have high energy density. So, of course, nuclear power provides that. Another is to focus on creating higher output assets. So, higher output wind turbines and solar panels. And in the wind area, I know that's already taken place. Larger turbines that can produce, more energy per turbine has already been a focus. Natural gas combined cycles, being able to, those assets have been built on larger scales, they've been rated output, bigger units have been built so that we can get a larger energy density for a given footprint. But I think this is an example of an issue which historically has been managed, but it hasn't really been a major driver of decisions, because we, generally speaking, have had historically a pretty good amount of land and water resources to utilize to support power generation, while not necessarily impinging too much on other economic activity. But when you think about the long-term sustainability that I've been discussing, this competition arises to become a more significant issue. And so anticipating that and mitigating that becomes an important issue. So this ultimately influences how you build your generation portfolio and how you try to structure it so that you have a healthy level of energy density in the overall portfolio. Just another aspect of these challenges. Long-term consumption growth. So, this is an area I think that's been debated a lot. Many of you who are familiar with some of the discussions over the last, I would say, certainly the last 5 or 6 or 7 years, if not the last 10, there have been a lot of studies that say that, when you look at energy efficiency measures, just more energy efficient systems in our society, whether it's in appliances or equipment, that electricity demand actually is leveled off. And that, there have been a number of studies that have suggested that electricity demand is going to remain fairly level for a few years, not 30 or 40 years, but 10 years or something. I think those studies have validity in the sense that they are looking at a set of conditions which could lead to a period of time where demand growth in certain areas can be pretty flat or not very fast. But the question here is really not that. The question here is what consideration should be given to where consumption growth will go over basically the indefinite future. So you have to think about very long time frames. And when you look at those kind of time frames, very clearly, consumption essentially is driven by 2 fundamental variables. One is just how many people there are, and that of course is closely connected to the scope of economic activity. In the U.S., our economy has generally increased electricity intensity generally over the long term. And if you look at the way our economy has been transforming, we're likely to see continued growth in electricity consumption because our economy is shifted away from some of the activities where primary energy consumption is the primary need. So if you have to think about what the long-term consumption will be and anticipate that, it's very difficult in the power sector to respond to a growth in the need for electricity rapidly. A lot of lead time is needed to address that. Another facet of this question about long-term consumption, which I think is very important to think about, is what happens when we do create efficiencies that reduce electricity consumption? What typically has happened? And I think the analogy here is very much like if you have an investment portfolio, say you're saving for your retirement. If you make more profit on an investment than expected, typically what is done is that profit is not simply saved, it's invested somewhere else. That opportunity is to use that resource to invest it somewhere else and generate more growth is done. That's been shown to happen in the electricity sector or in the economy frequently, that when, for example, if you, I always use this example, if you take a business owner, say someone who runs a chain of restaurants, for example, or perhaps a chain of some sort of retail business, and energy savings technology results in lowering the cost of energy for that business. Often what happens is the business owner will say, well, I have an opportunity now to expand. I can open another facility because I can afford that, and I can there create economic opportunity by virtue of that. So the sustainability, but my point of this is the sustainability of reductions in consumption by creating policies or incentives or even regulations that can control behavior of consumption. The sustainability of the savings that you can get from that, I think, is very, very uncertain, because of this phenomenon of a desire to reinvest that saved energy essentially as an asset. Therefore, I think we have to look more at how do we meet the consumption growth? How can we successfully meet that growth and provide it, rather than create strategies that focus on, well, we're going to make sure we just don't use very much energy in the future. I think that's desirable, but that's not alone a sufficient capability. So that then takes you to several important considerations, which are, again, I'd say these areas are somewhat already recognized in some of the research community, but they are, we have so much focus now lately in how the electricity delivery and consumption side of the grid, a little attention is, I think, moved away from the areas about how can we generate more electricity. So one area is figuring out how to anticipate and plan growth. Where is it going to come, and how much growth are we going to need? What rate of consumption growth will occur? Spending time thinking about that is very, very, very important. And I think those timeframes have to be thought about in much longer timeframes than 10 years or 20 years. For example, if you look at the annual energy outlook, which the Energy Information Administration produces every year, many of you may be very familiar with that, but it's a very heavily relied upon annual report representing kind of the DOE's perspectives on a lot of questions about fuel consumption and costs and electricity and so on. They don't have, there's some discussion about long timeframes, but the detail tends to be very focused on comparatively near-term issues, in the next decade or two. And so extending the horizon of the planning around where asset growth or generation capacity growth is needed, very, very important. And that again takes us back to the framework for looking at analysis of how that growth can be met economically under the various constraints we have, regulatory and so on. And that takes us back to some of the modeling that we've talked about. An added layer also in this challenge is that, and it's an opportunity, is how to tie the analysis and modeling of this anticipated growth into asset planning processes that power companies use. Because at the end of the day, the organizations that actually build these assets, that figure out what it's going to take and when to build an asset and where to site it, are primarily power companies. So we have to tie in whatever research is done to look at this very long-term consumption growth. It has to be integrated with how power companies do asset planning. Of course, the transmission network itself is a very important asset in taking advantage of what capacity we do have and new capacity we build. So there's sort of a companion priority around how to anticipate the changes and growth in transmission interconnection to accommodate the utilization of the capacity that we have and would develop. This kind of ties back earlier, as I was saying, to the just-in-time problem. The enhancement of the transmission network can help you mitigate the problems created by that just-in-time network. Resource adequacy planning and tools. This is the area where when you have an unexpected condition where demand is high or a subset of assets are unavailable, you're going to have adequate resources. That's there's added complexity in that issue when you consider all over the time frames we're discussing here. So that's another facet of an area where breakthroughs in looking at that consumption growth would have to inform what a long-term projection of resource adequacy needs are. Another way to think about this long-term consumption growth is ask the question, what assets are we not taking advantage of, or what are we not doing that we could be doing? And of course, coal is moving out of the generation portfolio now for environmental reasons and a few other reasons too. It requires continuous fuel supply and so on. And environmental controls for coal seem to be so costly and problematic that I think the solution has been to move away from coal to other assets. But in the long run, I think, now I'm expressing an opinion here, but I think analysis will support this. In the long run, the scale of consumption growth we're likely to experience, even at a moderate rate over long periods of time, is going to place our society in a position where we're going to have to utilize all the assets we have, all of them. And so we're going to be looking, I think, someday at how to take advantage of coal, because it is a considerable amount of energy is in coal, and it's an asset that's available. So I think it's best to anticipate that and ask the question, how would we utilize that resource if we had to? And at what cost if we had to create the environmental controls that are needed to make it feasible to consider that? And of course, that creates a lot of secondary problems. Well, how would you operate a coal plant with CCS flexibly? That's definitely not a problem that's been solved. And finally, a very important feature of the modeling, energy economic modeling I've referred to several times, is that there is a sort of a yin and yang to this. There are many difficult problems with how am I going to deploy an array of assets looking at the next year or two of demand. In the near term, we have a pretty good idea of what demand patterns are going to be. You have to think through where all the assets are, how they will be deployed, whether the transmission capacity is there and available. Tying in the recognition of those sort of operational and dispatch challenges with a long-term modeling process, which can allow you to say, well, as our fleet changes to respond to different challenges, what will the unit commitment challenges look like in, say, 30 years? Integrating those two is a very important challenge that should be looked at. And if it were, we would be able to do a much better job of understanding how to meet these long-term problems, but maintain operational viability at each stage in the future. That's a challenge that's largely not fixed. It's become a focus of energy economic modeling in recent time, the last 5+ years, or maybe 10 years the most. But it is definitely a sizable challenge, analytical challenge to achieve that. But if done, would provide a huge capability in terms of understanding how to address this long-term growth while meeting all of these short-term needs that we have to meet on an operational basis. So a lot of dimensions here. I've gone through many, many different facets. So what I just kind of want to do is provide an overarching perspective now on all of this. Any one of these areas, obviously, themselves is a topic of lengthy investigation and discussion. But what I want to do is kind of create perspective. So obviously, a lot of different things need to happen, or could, if they did happen, would really create much more opportunity to achieve the sustainability that we've been talking about. So I kind of organized sort of the main threads of some of those things that I've discussed here in a kind of an ascending level of greater difficulty. And this obviously entails some subjective judgment on my part. None of these things are trivial, but if you look at the top here, there is a lot of work already being done on how to make assets cheaper to build, how to make sure they operate more cheaply and they're efficient. There are many technical challenges in that, and that work needs to continue. But that's an area, at least, where we've invested a lot of time and effort to understand how to do that. So some headway is being made. Secondarily, if you go more down the line, as a result of that, work has been done to figure out how to establish that assets can run longer periods of time. Work is underway in that area, and that is really good. And that's why I would put this at the same slightly more feasible in the spectrum, because resources are being invested. This expanded energy economic analysis has already been used and started to look at other problems besides just solely the question of least cost electricity production. But a lot of work is still yet to be done on how to expand the base of that analysis so that it can address some of these other questions, and also to create that platform on which the stakeholder discussion can be had that enables agreements and consensus to be built. This operational flexibility issue is very important, not only as a problem, but as a capability. The more capability we have, the more flexibility we have to contend with the different environmental and economic challenges while continuing to use the assets we have. And there are many underlying technical issues that emerge out of that fundamental need for operational flexibility. How to use nuclear plants in a flexible way there's a specific strategy for doing that. You can't really vary nuclear plant output on a moment-to-moment notice, but you can plan sort of periodic up and down output levels, which address patterns of variability that occur over days and months. heat recovery steam generators. That's what the acronym HRSG stands for. They're in that sub bullet. HRSGs were not generally designed for a lot of flexibility in their changes. So the thermal and mechanical cycling that flexible operations creates has impacted HRSG reliability negatively. Addressing that issue will really increase the value of natural gas combined cycle assets. And then, of course, as I said earlier, someday we're likely to face the challenge of using coal. And therefore, we're going to probably have to have CCS. And if we're going to have CCS, we're going to have to figure out how to run a coal plant with CCS cost effectively and with flexible capability. Big challenge. Looking at the whole portfolio of assets as something that needs characteristics that have higher energy density, so we don't get into situations where supporting resources, water, land, and so on, are available to the generation fleet. We don't want those things to become limitations. That leads to some different philosophies about how to build the portfolio. That's probably, I put that further down on this list as one of the challenging things, because that means stakeholder agreements on how to change that composition of the portfolio to achieve that energy density will take us into domains that aren't purely technical, but in terms of policy space and so on. I've already talked about coal and CCS as just a technical challenge to do that. It's a big challenge. CCS technology has a long way to go to get to the point where we can meet some of the aspirations that I've kind of described here. And then finally, in my mind, probably the grand challenge maybe is this goal of decoupling generation consumption, or at least partially doing that. And by doing that, creating the ability to operate and produce electricity in an optimal manner, which is not constrained by how we consume electricity. Were we able to do that, I think we would create huge opportunities to increase the sustainability of our overall portfolio of generation assets. So this perspective of what needs to be done, what I really want to illustrate here is the waterfront is broad, and we need to be looking at a lot of different things at the same time if we will hope to achieve the sustainability. There isn't really a few key things to do. You have to look across a wide range of things, and this is where probably the overarching theme of my whole group of presentations is to bring attention to this idea that I would like to encourage people in research to pursue a waterfront of things and to communicate the importance of doing that, because I think that's the shift in thinking that's needed to address some of the challenges that the portfolio has. So what I did something here to try and tie together this overview here a little bit. I thought about all these different challenges, and I just thought, how can I visually sort of communicate the sort of interconnection of them all? So what I've done here is I just tried to just give one view of way to think about that. We have operational needs, we have existing assets, we have future assets. They're all tied together by different technology capabilities, storage, flexible operations, different ways and scales in which we deploy assets like small modular nuclear reactors, so on. So that's all kind of the fleet operating it, producing electricity. Within all of that, there's the market design in which these assets operate economically. Those market designs today, some of you may remember my previous presentations, I talked about how the markets have evolved mainly to produce lowest cost electricity. They have added features because people recognize, well, we've got to make sure that we have adequate capacity margin to deal with surges in power generation, or we have to ensure that our rules require we produce a certain amount of electricity by renewables, so we have to put in market features to ensure that happens at specific times. So these markets have these added features which affect how assets are operated and what assets are deployed at any given time, or dispatched at any given time. So that's an overarching set of constraints that operates on the overall array of generation assets. And on overarching the market designs are our energy policies, which set our aspirations for what we're trying to achieve. Obviously, we want to produce electricity, we want to produce it cheaply, but we want to do that while meeting environmental constraints and people who can make money doing it, and so on. So these overlays, I sort of depicted these things as overlays on the overall sort of technical environment of generation assets and their operations. And then the italics just kind of call out some of the opportunities for addressing issues that would increase our ability to have a sustainable generation asset mix, given the way all these things tie together. So this is just one view of it, but I think what you can see here is, again, we need a waterfront of priorities to achieve a sustainable environment in which we're producing electricity for the long term. Okay, so you've suffered long enough. I just got one last slide here. We can have some discussion. Summary. I just want to summarize and say, look, I think there are some very substantial challenges, and I've tried to move around here to give you a feel for that. But there's a lot of work's been done. A lot of work's been done in several parts of these challenges. So we have a foundation, and that foundation is substantial. So there's some progress is being made and can be made. We just have a long way to go, but there's a foundation here that's very good. I think calling out the energy economic modeling is really important, because I think a lot of our barriers to making decisions addressing the sustainability are barriers related to misunderstanding of priorities or perceived ideas that the objectives of one stakeholder group have to be sacrificed for another stakeholder group to get their objectives fulfilled. We need to create a way to communicate and reach informed consensus on where we want to go. And obviously, in my mind, I think primarily policymakers and regulators as an audience for this, but it includes all the other stakeholders as well. I think there's an environment in which there may be a little more receptivity for having this very broad, broad scope view of all the things we need to do to achieve sustainability, because global climate change and some of the complexities that have emerged from interconnected energy markets have created a receptivity amongst policymakers to listen to discussion and about this. And so I think we have with the emergence of the climate change issue, now over 10 plus years ago, I think in the public consciousness, there's an environment in which there's an opportunity for the technical community to maybe make some headway in communicating these needs across this wide array of dimensions. I think, while all these things, some of these things I've discussed are very challenging, I think there's an opportunity to positively affect sustainability. We can make headway there. And I think, rather than interpret this as, wow, it's not very likely, I think we should interpret this as there's a lot of fruitful directions for research and development that can take us towards the sustainability. So I think that's kind of the underlying thrust, I think, where electricity generation research and development ought to go. And then finally, I think there's a synergy here. If we achieve a lot of headway in one or two of these areas, addressing one or two of these challenges, that will certainly be beneficial. But I think that you can all see that there are so many different dimensions of what constitutes a sustainable electricity generation portfolio. We need the synergy of addressing these areas in these multiple areas. We need these multiple game changers to get that. And I think that's, again, this waterfront idea. We need to look at the big picture rather than look for a silver bullet or a focused couple of things, even though that's a much easier way to think about it. Okay, so quite a lot there, but I'm going to stop at this point, and maybe we could entertain some discussion and questions.
Wow. Excellent talk, Revis. As we do normally in these seminars, we first entertained questions from students, and you could either articulate those questions, in other words, unmute yourself, introduce yourself, and then ask a question. And then we'll work our way to the rest of the audience. If you want to use a chat box to insert your question, please go ahead and do that. Susan or I will go through the questions and present them to Revis. Revis, again, a very, very informative talk. You covered a lot of territory, and only you could stitch them in a way that everybody could really be captivated by it.
Well, Ramesh, can I make just one brief comment? I realized that this could feel like this is just a shotgun pattern of issues to people, but I think I just want to emphasize that there's already a lot of opportunity to focus in an in-depth way on any one particular technical area. If you're interested in transmission, for example, what I think is not thought about as much is what holistically has to be done. And that's why I chose to create this kind of mode of presenting it. Because I think emphasizing the interconnections between issues is where I think more opportunity to think about new ideas and make some impacts are. So that's the idea here.
Good. All right, questions from students.
I have a question.
Yes, Logan. Introduce yourself.
Hi, I'm Logan. I just wanted to know, how do you see the grid adapting to the integration of electric vehicles, and in terms of being both a load to the grid as well as a supplier of energy storage?
A great question. It's been a discussion. It's been an issue that's been talked about a lot with electric vehicle research. First of all, it will definitely be, I think, a factor that creates more load variability, more demand variability, like I was talking about earlier in the presentation. Recharging of vehicles, how vehicles are used. If we do successfully penetrate not just the personal vehicle market, but more of the sort of short range distribution system is relying on electric vehicles, not the vans and things that we see. That's going to create variability because all those different businesses are going to be utilizing the electricity grid at different times. So there will be more variability, and that translates to the operational flexibility challenges that I was discussing earlier. So that's one side of the equation. I think the opportunity to see vehicles as a kind of a pool of energy that could be drawn upon as a resource is an interesting idea. I think there is the aggregation of those things, kind of like I said earlier, distributed energy resources could potentially be aggregated in a way. And if they could be dispatched, you might have the opportunity to buffer the just-in-time demand issues from the generation. The interesting question with respect to vehicles is, can they be aggregated at times? Is there a way to create a construct where a coordination can exist? Because the ultimate question with any kind of aggregation of a distributed resource is, can it be dispatched? Can at a given time with relatively not that much lead time, can you say, we need to dispatch this much energy? And so the really interesting question is, how could you achieve that coordination so you have that dispatchability? That's the key attribute. That might be possible. I think that's a very rich area to look into, but it is achieving that dispatchability that's really key.
Good.
Thanks for the question.
Questions from from students?
To go off that last point, I'm Nick, by the way. I'm an ESE student. So if you have electric vehicles and if everyone's driving home, say at 5 p.m. and they plug in their car, and I feel like that potentially could lead to even worse peak demand. So I don't know if there's anything being done currently to kind of think about that.
I think I first, let me just qualify this by saying, electric vehicles and all of the underlying sort of, let's say, infrastructures around that is not my expertise. So I don't want to claim that I have comprehensive knowledge there, but I agree with you. I think basically just the way things are now, people go out and buy electric vehicles or hybrids, and they're going to do what they do as far as recharging whenever they want. There isn't any really constraint on when that's done. So I think from my perspective, one would have to plan for potentially higher, steeper peaks in those periods of time, and have a system that's capable of responding to that. I guess technology might solve that problem. Perhaps there's a strategy where a person comes home and plugs their car in, but it doesn't necessarily make an immediate heavy draw right away. Maybe there's some way in which you create a technology which charges the car in a way that spreads out that load, or there's some communication that could occur between vehicles and the grid, so that could be controlled. Maybe if customers would accept that, there might be a technology solution to that. I'm not sure.
Good question.
Thank you.
Any more questions from students? All right, I want to open it up to the audience. Questions for Revis?
In the chat box, Rudy.
Okay, why don't we go through the chat box?
Frank Richards asked, he want to comment on crypto mining as an unanticipated energy hog.
Yeah. Okay. You want me to make a comment on that? Well, let me interpret. I'll interpret the question as that maybe Frank is interested in what type of challenge that might pose. That's a calculation actually I haven't done yet. I wanted to sort of estimate kind of what that load is. I think from what I have read about this issue of cryptocurrency and the underlying computer load that creates in order to keep the blockchain essentially intact, I think that today may not be at a scale where it's likely to be significant on a grid scale that we're talking about. But I think if you extrapolate cryptocurrency growing, both as an investment opportunity, but also let's say cryptocurrency ultimately achieves its goal of becoming currency, then it could create a much bigger load. I think I kind of maybe would subsume that under this larger question of demand growth that results with increased electrification of our economy. Maybe cryptocurrency would become a new driver within that overall issue of increased electrification of the economy. I think this is a speculation on my part because I can't say that I've really tried to analyze this yet, but I would guess that aggregated over an entire economy, the level of load growth associated with cryptocurrency is probably something that will have a somewhat predictable curve, and you can probably then try to analyze how great will that demand be, and therefore what kind of assets are going to be needed. That's my first impression, as opposed to highly variable. But I think that's an area that probably should be looked at in much more depth.
So Susan, you want to take the next one?
Alexander Vincent. He said in New Jersey, the state EPA is working on expanding the oversight of the Clean Air Act and federal EPA guideline by enacting rules that require electric boilers / heating devices for 1 MMBTU to 5 MMBTU. These are not small boilers / heaters and would use a lot of electricity. Do you see this type of regulation spreading across the country? And how do you see this or other behavior changes to electric devices impacting the sustainability and power generating fleet? It seems this could have a huge unplanned demand that by traditional power sources.
I wasn't aware of the specifics of New Jersey trying to sort of apply additional requirements on boilers. I would have to say that I haven't. Well, actually, this is a very complicated question because there are a lot of layers of regulation and involvement from the state and federal level. In broad view, let me break this down maybe into two parts. The first part is, what is this a trend that other states will go into and what might happen there? And the second is this being an unplanned impact on the generation fleet. From the first part, I think obviously under the Trump administration, the EPA was weakened, and the EPA's leverage of the Clean Air Act and other established law as a tool for going further into regulating emissions from different sources, that slowed down a lot under the Trump administration. I'm not really sure what's going to happen under the Biden administration or ones that follow. But I do feel, as a broad rule, that it seems to me that states have stepped in and filled that void a little bit more, because I think there is still a perspective, at least in some states, that certain levels of regulation are needed that may have been somewhat abdicated for, at least temporarily, by the federal government. But I have to say, I'm not really aware of like a groundswell of that happening across many states. So I'm not sure how representative what's happened in Jersey is of other states at this point. So apologies, I'm probably not as familiar with that as I should be. The other facet is, what does this represent for the generation fleet, and what could happen? I think what this probably will result in ultimately is increased demand, simply because I think if there are requirements imposed upon emissions or other impacts that individual components create, like a boiler or some other type of equipment, that will translate, my guess is, to less efficiency in terms of energy consumption, and that will therefore translate into a more energy needed for a given amount of functionality, whether it's a boiler, it's heating, or whether it's a motor, or whether it's some other component. Generally speaking, what I have found is that when requirements are applied, which desire to reduce an impact, noise, pollution, whatever it is, it usually leads to reduced energy efficiency of the device, and that tends to then lead to more energy requirements in order for that device to achieve its function, run for a period of time or run at a certain level or whatever it is. So that's a pretty broad answer. I'm sorry, I can't be more specific to your case, but that's what I would anticipate.
Okay, we have another one. I'm sorry, another one for, did you want to say something, Rudy?
Yeah, I just want to say the same, read the questions, just relieve you a little bit. For natural gas peaking plants, what kind of time frame is needed to bring it online from a cold start? How flexible is a gas plant to vary its output?
Okay, great question. Outstanding question. First of all, you from a cold start, okay. Well, every one of these assets has limits, obviously based upon not creating equipment damage due to thermal transits or mechanical transits. So having said that, a natural gas plant can start up faster, definitely a lot faster than any of the other sort of, I'd say, mainstream options, thermal power options. I think it's probably hours from a cold start to reach a reasonable level of output, not days. But I think that I said we, slipping back into my past, but when I was at EPRI and I was involved in a program looking at flexible operations, I think that what we found at that time was that because of the needs of the grid, operators were pushing the limits of those timeframes for what it would take to get from cold start to a given output level, or more importantly, turn down factors. You have plants running at an output, say 8% of what its output is, and now for a period of minutes or hours, it wants to reduce that output by a third or half. And then within another several hours, you want to come back up. That isn't necessarily outside the capabilities of the asset, but it is a level of cycling that was not anticipated as a frequent occurrence, and therefore it has a cumulative damage on a lot of the components that wasn't considered in the plant's design. And I think that's true with gas units. Obviously, a pure gas turbine, essentially a jet engine, has more dynamic design, but like the natural gas combined cycles and so on, certainly we're not thinking about that type of cycling when they were designed.
I do see somebody with a raised hand, Udaim. So did you want to ask a question? If so, please unmute yourself. Udaim, did you have your hand raised?
Yes. Good day.
Hi.
Are you hearing me?
Yes, we can hear you.
Okay. I wanted to ask, looking at the industry, like a cement manufacturing industry and the heavy duty equipment they use, like 11 kV slip ring induction motor, which are high power consuming equipment. Do these policies look at their impact on the energy market?
So, okay, so I understand the description of the, these induction and the demand that it draws, or a current draws and so on. But your question is how this type of demand affects future policies? Is that the question?
Yes.
Okay. So, yeah, I think this is really another aspect of flexible operations.
Okay.
I'm sorry, I interrupted you. Go ahead, say that again.
No, I'm just following what you're saying.
Okay. So let me continue. I think this is another facet of flexible operations in the sense that if we have technologies which create more dynamics in starting up, so like a big current draw or an inductive load, whatever it is, then you essentially are creating more variability in demand, and therefore that just translates to a stronger need for more flexible operations capability. That in turn then translates to designing a generation fleet which has more operational flexibility capability within it, which can be met by a variety of different combinations of technologies. Like what we've done now is we've just gone to more and more natural gas, because that's comparatively more flexible than the other assets. That's how we've done it so far. Another thing is, as I said earlier, creating more operational flexibility in some of the other existing assets so that we continue to use them for their other benefits, or addressing the transmission network so that we can move power to meet flexible changing demand needs rather than having to rely on flexible operations of assets within a given area. So I think your example really is a specific example that supports, where technologies are emerging that create more flexible operation needs.
All right, so again, going back to the chat box, carbon capture for CO2 for emission reduction is an acceptable innovation. Is the energy sector looking towards that as a form of sustainability?
I think definitely carbon capture is being looked at very hard in the electric power sector. I'll not say the energy sector, I'll focus on electric power. I think the real challenge there is trying to lower the energy cost of, once the carbon dioxide is captured, freeing it up and storing it so that you can continue to capture more CO2 in a process that produces it, that energy cost is very high. And finding a technology where that energy cost is lower has been the primary driver of the research around CO2 capture. The methods for doing that in the process industry, the energy costs are acceptable for those applications, but are not acceptable in the power sector for the scale on which we would have to capture CO2. So while there are established ways to capture CO2, they don't scale well for the electric power sector. So it is definitely a high area of interest, and a lot of efforts being invested in trying to find viable technologies that work for the power sector.
Okay, we still have some time. Any more questions? The chat box is empty right now. So, you have any more questions for Revis? We got a few minutes.
Hi, this is Frank Richards. Can you? I'm really curious about this the New Jersey law that is going to take. I mean, it's 100% efficient because you're going to get a whole. $1 of energy is going to heat $1 worth of whatever water, but intrinsically it's going to be using something that's maybe 30 or 40% efficient at best. When you're if you have to use gas, which you will have to use gas for a long time, or coal or oil for many years into the future here. How can we use our heads and allow this to happen? I'm very to me I'm incredulous.
Yeah, Frank, I mean, without venturing into editorial comments about the prudency of different policies, let me just illustrate. This is where I'm going to tie this back to all these words I was saying about creating a framework for stakeholders to resolve issues. I think you have a narrow focus on a particular issue. Maybe somebody decides the way you need to heat water is more efficiently on a small scale as this, and they don't think about the trade-offs that occur in the broader system as a result of that. And I think these kinds of policies that could have that kind of a very localized benefit, but in a broad sense, maybe a negative impact. Those things can occur because we don't really have a very good framework on which these multiple scales or levels of impact can be looked at together and objectively assessed. I can only tell you, from working with the regulatory groups and the policymakers I've worked with, a lot of these people, I think, understand what the trade-offs are, but the tools they have to understand those trade-offs are just very limited. They have advocates telling them, from a very narrow perspective, you should do X, Y, or Z, and this will happen. That's good. And they don't really have a framework, a larger framework to evaluate what they're hearing. And so my way of responding to your comment is to simply say, I think this is why we have a really high priority to create some kind of analytical framework where an objective discussion of trade-offs at all levels can be seen. So if we do this, say at every state, how would that translate when we look at the overall grid or over a longer period of time, or whatever?
I see Nate Nichols has his hand up. Nate, please unmute yourself and introduce yourself, please.
Yes, Nate Nichols, ESE grad from 2012. And so my question is kind of more, there's students on here, Revis, where or how, should students be looking or other engineers be looking to maybe get involved with some of the policy challenges and such? Is it getting plugged into just their company and whatever
Right.
company they get into, or is it getting involved with industry groups, et cetera?
I think there's multiple entry points to that, Nate. I think, I don't know if I have a convenient, comprehensive answer to your question, but let me just maybe briefly recap how I've gotten to this place where I'm at, and then maybe draw a couple of generalizations. I'll probably be brief. My background started out as power plant design and construction as a nuclear engineer. And then I eventually spent most of my career at the Electric Power Research Institute, where I became exposed to, technically speaking, I was involved in technology research to other generation technologies, coal, gas, renewables. So my pathway was getting involved first in a technical area, then broadening across multiple technical areas. And that led to recognition that some of the drivers behind the technical problems were not entirely technical issues. They were policy issues or economic issues. So that drew me into research areas where I was starting to understand how those policy and economic issues created opportunities or problems for technology research. That in turn led to jobs where I spent time actually interacting with decision makers in policy space. So I think as an engineer, if I was like, say, if you're a student or you're an early career engineer, what I would say is you do need a technical foundation to understand the basic role that different technologies play, say, in my case, in the generation of electricity. I had to first have some understanding of those generations, but I think the key is try to get involved in areas which look at how everything comes together. My pattern for that was the energy economic analysis work. I spent about a decade plus working with economists and others and started to really understand how you can see how the different technologies come together to provide the function that the power sector needs to provide, and how the economics impact that, and how different technology developments change the economics. I would say I stumbled into that over time. I started out thinking I would be a technical person, primarily, nothing but that. I would say if you want to be more involved in these policy discussions, you need to start anticipating, how do I understand how things are integrated and come together? And so having said that, I would say, pursue those opportunities in your educational period of your life, if you're still a student, or look for the function in companies that looks at policy advocacy, or looks at how the company establishes its positions related to different policies, and try to create a connection between the technical knowledge and the policy. I will have to say, though, not all organizations or educational institutions spend a lot of time on this connection. A lot of times it's somewhat holistic, which is how it happened for me. But that would be my answer, is try to anticipate having this broad understanding of how things integrate earlier on in your career and pull it together.
Well, that's an excellent answer and an excellent talk, Revis, and a good way to end this session. So I just want to remind you that next Monday, when we get back to the Monday routine, we'll have a presentation by the CEO of AutoGrid, how it works. And you heard a little bit about virtual power plants, and these guys are the proverbial 300-pound gorilla in that space. And so he will have a lot to share, how they got their business going and what are they doing? What is a virtual power plant? So it should be an exciting presentation. Also, if you want to learn more about the master's program in energy systems engineering, we do have an information session. Mark it on your calendar if you're interested, March 10th at 12 noon. The details are in the chat box, but if you are interested, look forward to seeing you there then. So again, next Monday, we'll have a seminar, and next Thursday, we'll have this information session if you're interested. Thank you, Revis, for this great talk. Thank you all for your attendance, and look forward to seeing you in future sessions. Bye.
Thank you, everyone.